So in many machine learning algorithms where we have a cost function that we want to optimize against to minimize the cost, we are going to use gradient descent as a method for optimization. Gradient descent is exactly like it sounds. The idea is we calculate the gradient of the cost and march down the slope that's dictated by the gradient to get to a new position where the cost function has been lowered. We're going to do this iteratively to finally reach some type of local minimum. We can think of it like descending a mountain one step at a time, where locally it might be very foggy, such as like in this picture, where we can't see all the way down the valley of the mountain, but locally we can see which way leads down. And we'll just hope that by taking this one step at a time and repeating it over multiple steps that we'll actually get to the bottom of the mountain. Many times we might want to choose our cost function to be a convex function so it only has a single valley. This way we can make sure that any type of gradient descent that we do is going to eventually reach the global minimum, regardless of the starting weights that we assign. Let's take a look how gradient descent works in a single dimension. We're going to come back to this credit line prediction problem and say that we're going to take the most important variable, which might be salary. Here we put salary on the x-axis, and we want to know how to regress the credit line from the salary. So obviously, lower salaries we might have lower credit lines, and higher salaries we might want higher credit lines. In doing linear regression, what we're going to do is fit a hyperplane, in this case a 2D line, to try to minimize squared error. Again, by squared error we mean to calculate the lengths of these lines' predicted value and square them, so that longer lines such as this one would be penalized proportionally more to its square. When we do regression on the univariate case, remember that we have two parameters, a theta 0, which is our intercept, and a theta 1. Because it's a little bit difficult to visualize initially, let's ignore the bias term. And let's just deal with the slope. In this case, we can draw different lines that originate at the origin. Each of these lines will have a different cost. We can see that the orange line gets the best cost because it's closest and has the least amount of error. This looks like it has a slope of 1. On the right-hand side, we can plot these costs, in other words, the squared error with respect to all of the blue distances for the orange line. This is going to give us a particular coordinate on the right-hand side. And we can plot the other values accordingly. For example, the red line has a slope that's much larger, but also gets more error. So we can complete the plot by passing different lines through the origin. This gets a little trickier to visualize when you go to multivariate cases, or even in the case where we insert the bias term back into the univariate case, which we're going to do now. We can think of generating a contour plot on the right-hand side where the colors would indicate the different types of costs that are associated with it. For example, each of the ovals in the right-hand side diagram has the same cost, but would represent different choices of both the intercept as well as the slope. Let's take a look at an example where we pick a good line. In this case, it would have a value close to 100 as the intercept, and the slope of approximately 1/2. So it would be right in the center here. You can also think of picking other types of lines. For example, what happens if we pick a line that has no slope but an intercept of 100? Or no slope and an intercept of 1000? These would end up approximately here. And you can see they have somewhat equivalent costs. By varying the slope and intercept, we would obtain different values that we can plot on this contour graph. This gives rise to the idea of where we want to do gradient descent, where we'll start with a particular set of parameters and then gradually walk ourselves down to the center where the cost is minimized. We're going to start our gradient descent by picking a weight vector initially. Let's call that theta 0. When we stick to the analogy that we're descending a mountain, we can think of ourselves as having a limited stride length, or fixed step size, which we'll call eta. And then our goal is to find a new set of positions or new weights that's a combination of the original weights, just with a pick of different places that we're going to go. The important thing here is we get to decide which direction we're going to go, our V. So we want to pick the direction that's going to minimize the amount of cost. We'll note here that gradient descent is a great algorithm because it can minimize any types of smooth functions, even ones with small even ones where there's some discontinuity in certain places in the cost function. Let's take a look at a visualization of this in action. Here you can see the original weight vector gives you a hyperplane that's not particularly good, one that looks a little bit like this one here. But over different iterations, it comes to a better and optimal hyperplane that minimizes the ordinary least squares. So how do we pick a direction V that we want to go in? We'd like to pick the direction based on We'd like to pick a direction that's going to maximize the utility that we get from taking that single step. In other words, the step that allows us to go down the most. To calculate this delta, we just simply take a look at the cost function before and after we've taken the step. Expanding out the first term, it's very simple. We'd be at the same position we were before, but after we've taken a particular step. Let's say that step on the diagram over here, we were originally at this position at time t, and now we're going to take a step in a direction that helps us achieve our goal of finding a minimum. When we expand out the first term, we are getting an inner product between the weight vector and a unit vector that we are going to determine. We can take the eta component and just factor it outside, and we'll have our linear term that we would get from the first order Taylor approximation, which is just the derivative times the step. We would also get higher order terms, but we're going to ignore them for now. We want to create V to be a unit vector, and to make sure that the unit vector does the most effect as possible, We're going to choose the one that gives us the steepest descent down the curve. Because we want it to be a unit vector, we're going to have to normalize it against its norm and choose the negative of the gradient so that we're descending instead of ascending. The final result is that we'll get the equation that we see here. Now, when we do gradient descent, we have to choose our parameter eta, which is our step size. If we make it a small number, that's fine, we'll be able to converge, but it could take us many iterations. For example, when we set it to a small number like 0.1 here, we would take 75 steps to reach the minimum value. Something more drastically bad happens when we choose an eta that's too large. For example, even though we have a convex function here, but because we've taken too large a step, we might actually overshoot the minimum. We might arrive at the other side of the cost function curve. If we continue to do this, we're going to ping pong back and forth and eventually maybe not even converge. The right thing to do here is determine the step size based on the slope. When the slope is obvious and there's a clear path for descent, we should take a large step. And when the slope is small, we should take a smaller step just to make sure that we're going in the right direction. This leads us to a better outcome where we can still converge but take much less steps than in the case where we use a very small fixed step size. This is the intuition behind going to a fixed learning rate rather than a fixed step size. I'm going to call this alpha. Alpha gets rid of our eta and just looks at the slope to determine the step size. So in summary, we have the logistic regression algorithm. Internally, we're doing the gradient descent algorithm, where the gradient descent algorithm can be applied to any cost function that's smooth and continuous. In the case of logistic regression, we're just using this particular form, which we're going to discuss in our post-lecture. Just to be clear about it, let's recap the steps. We're going to first initialize our weight vector at the first iteration to some number, for example, a vector of all zeros. Then we're going to compute the loop. That's going to allow us to find the appropriate weights. To do this, we're going to find the gradient and then update the weights to move in the direction where the new weight vectors are determined by the original weight vectors plus the step size that's dictated by the gradient's magnitude. When we've done that, we've found our optimal weights that we can get, and we're going to return these to the user. So when do we decide to stop doing gradient descent? It's rarely the case that we actually get a gradient of 0 and we know we've reached a local minimum. But we can try to choose a small threshold such that if the gradients become smaller than that, we would stop. However, this is not a good idea for several reasons. Because sometimes there are regions of the cost function that might look flat, but in fact have a small gradient that eventually will allow us to go down again. For this reason, often we'll use other criteria to check that error itself is small or the maximum number of iterations is reached. Sometimes we'll use a combination of all three of these to decide when to stop.